Now that we understand what it means to look at limits at infinity, we might want to talk about how to evaluate these algebraically. If we have a rational function and we want to evaluate a limit tending towards infinity or negative infinity, one of the techniques we can use starts by looking for the highest degree term in the denominator. Then using that term to multiply the entire numerator and denominator by it. So our highest degree term in the denominator is 2x. We don't really care about the 2, we care about the variable. So we're going to use the x as a reciprocated term to multiply through the entire numerator, the entire denominator. We'll do a little bit of scratch work to clean this up. Multiplying 1 over x to every term in the entire function allows us to reduce some of these factors of x and simplify. So now we're going to rewrite our limit using this simplified version that we've manipulated algebraically. And notice that we're going to see limits of the function 1 over x. We know that as x tends to infinity, 1 over x tends to 0. So any term that has a factor of 1 over x essentially goes to 0 when we allow x to go to infinity. The only thing that's left from our function is the 3 on top and the 2 on bottom. That's a constant. We're looking at the limit of a constant, and x traveling to infinity has no impact on that constant, so our limit is equal to 3/2. Let's try another one. Here we have 3x squared plus 2x divided by 4x cubed minus 5x plus 7, and we would like to evaluate the limit where x is tending to infinity. We're going to start with the same first step. Find the highest degree term in the denominator, and then use that to multiply the numerator and the denominator by the reciprocal of that term. Again, we don't care about the 4, we just care about the fact that it's x cubed in the denominator. So we multiply through 1 over x cubed to every term in the entire function. This will allow us to simplify and then rewrite our limit using this manipulated version of the function. Anytime you have an x in the denominator with a constant on top, that term is going to go to 0. So the only thing left is 0 on top and 4 on bottom, which results in a 0. 0 divided by 4 is 0. In this case, we looked at a function where the degree in the denominator was larger than the degree in the numerator. If that's true, your limit when x is tending to infinity will always be 0. Look at another one. Now this one's a little bit tricky because our denominator involves a square root. So if we wanted to evaluate this function's limit, where x is going to infinity, we would still start by finding the highest degree term in the denominator. Notice that it's the square root of 4x squared. It's not just x squared. So we're going to multiply the entire numerator and entire denominator by the reciprocal of the square root of x squared. So every term gets a factor of 1 over the square root of x squared. And it's true that you can simplify the square root of x squared to just be x. However, when we sneak that term into our denominator, leaving the square root on the x squared allows the x squared to enter into the larger square root notation in our denominator. So notice that in my scratch work, in the numerator, everything says 1 over square root of x. But in the denominator, because I've snuck that inside of the square root, it's now just 1 over x squared. The square root on the entire denominator is taking care of the square root that I used to have. Now we can simplify, rewrite our function, and then bring it back up to our limit. Again, anything that has an x in the denominator with a constant in the numerator tends to 0. The only thing we have left on top is a 3, and on bottom it's the square root of 4, so our limit would be equal to 3/2.